Okay, first of all, I just want to highlight that analyzing the graphs is also a little bit about evaluating, determining what is the most significant thing and what you're going to focus on, and then it'll lead into solutions. That it'll lead into determining what problems are and how to create them. So we're really looking at the highest levels of thinking here, and so you generally find things get much harder as you work your way up, and you've got to build upon the lower levels. So it's often sometimes written as a pyramid because the knowledge is the foundation. Okay, also just to define these terms in the simplest ways possible as well for your writing. So accuracy is basically, is it correct? Is it the true result? Precision is how far above and below those results are when you're getting those measured. So the measured values, are they close to it, or are they going up and down quite a lot? So too far above and too far below quite often. Validity is the experiment really testing for what you are trying to test for? An example of this would be perhaps if you were reacting like magnesium and you're trying to increase the surface area, and you cut them into smaller pieces to increase the surface area, but they end up clumping together, so it actually decreases the surface area. So you're not really testing for that. Another example is maybe just not controlling your variables. The temperature's going all higher than what you said it was. Maybe if you're trying to use smaller pieces to increase surface area, but you're actually decreasing the concentration because you're using a smaller piece. So basically the experiment's not really testing for what you said it was testing for. The dependent controlled variables are not there. Reliability is, can you repeat it and get the same results? So it can be related. A lot of these things can overlap, which is the confusing thing. I've tried to give very simple explanations that clearly differentiate the four terms. And so it might not be reliable, especially with biology. If you've got, humans, especially psychology experiments where they purposely do the wrong thing just for the sake of it, or just something else is going on that the cause and effect is. The validity might be an issue, and that might affect the reliability. So an example of reliability, just basically something wasn't controlled or even stated, one of the controlled variables. All right, so moving on from there. This one's just basically, this is the experiment. It's just an enzyme experiment collecting the gas. So the faster it reacts, the shorter time it takes to collect the gas. So this is the data here. You can see that this one's temperature. So as the temperature is increasing, the time for it to collect is decreasing. And so these are the results that we got here. Just quickly, make sure you use those calculations here so you can copy and paste them down. For standard deviation, that's the formula I used. Absolute, which is 1 standard deviation, so that's 68% of the data. So that's for biology. Absolute uncertainty, the mean, is just half the range. There's the formula up there for you. So that's more chemistry, physics for that. Standard deviation tells you a lot more, and you can do a lot more. There's things like Westgard rules and stuff you can apply. There's a lot more research and understanding that goes into that. Absolute uncertainty, the mean, is a little bit more cruder. It's just half the range, which is fine. Always used, you can for chemistry at least, just grab the biggest one and apply it to all the data. And basically what I've done here is I've basically just shown you what it looks like if you use instrumental error versus standard deviation and absolute uncertainty, the mean. You can see that these error bars here look very similar and they're much larger. So always go for, you'll probably have either instrumental versus absolute for biology, or instrumental versus standard deviation for biology, or instrumental versus absolute for chemistry, physics, and choose whichever one's bigger. And for chemistry at least, you can even just go ahead and just use the biggest one. For physics, they like to do this, and I like to see this in chemistry too. They like to show you the individual errors for each point, which is far more superior. How do you do that? Just briefly, it is in some other videos, but you go to custom, double click on this line here, go to custom, specify value, and you grab the range and then delete this and make sure the two are the same, and that'll give you the individual values. All right, another thing that physicists like to do, which I'm actually sort of pushing for in chemistry as well now. So I'm sort of, they always do a better job in physics, and I'm sort of adopting a lot of that stuff, is potential percent differences. You can see in these formulas I've put dollar signs there. That locks that in, so I can copy and paste all the way along, and then I have to rewrite a new formula and copy and paste all along, and that locks that in, so Excel doesn't change those ones, whereas it will change this as you copy and paste across. And so this is a good way to work out what's anomalous, rather than saying, oh, it looks good or bad, or it looks too high or low. You can't actually tell when you're plotting the averages here anyway. And so generally if it's greater than 10%, but there's no black and white to this. There's a lot of judgment and evaluation. I've made up this data. So you can see here, that one is quite significant. You can justify deleting that value out now, and you will get a better lines, better line of best fits. I've also added a systematic error. You can see it's generally increasing. Did you spot that? And there's other issues here that basically it's your judgment to see whether that's significant. Did something happen here that you can talk about, that you know about? You have some anomalous results you could talk about and explain, maybe delete. So they're things you can do when you're analyzing graphs. As you can see here, so let me just go through the points here so I don't forget. So I've already talked about which one to choose. Choose the biggest one basically, and how you do them. I just showed you those with the formulas. Always match it with a scientific theory. It might be a calculated result that you have to do. For this one, it's the rate of reaction is slow to start with. Basically just due to temperature, rates of reactions for the catalyst, but there's actually denaturing, so there's a sharp drop off. Now, because this is in reverse, what we should see is this is showing us a line of best fit, but if you look up the published results, you'll also see that catalase usually denatures. It fully denatures around 60, usually starts to denature around body temperature. I think for plants, or definitely extremophiles can go up really high, but for this it probably should be, this looks okay, it should be like a slow, should reach an optimum and then rapidly decrease about here. And so that's something you can talk about, what are some errors in your experiment that meant you didn't get what you should have got, which is basically the reverse, sort of this flipped. So it's slow and then pulls straight back up and takes forever because it's being denatured. So if I apply a curve, funny enough, the R squared is better. So 0.84 goes to 0.93. So that is a better fit, and that does actually match the scientific theory as well. So you can't draw a line. You can go with this, but you can certainly justify imposing a line if it matches the scientific theory. For this particular one, you find that once you do this, it does actually, the error bars do overlap, so there is much more confidence also, not just in the R squared, which is arguable what's a good R squared value. Generally I'm used to above 0.9, but some people can argue 0.7 depending on what research you're looking at. But you would expect that the line of best fit will go through all of the acceptable uncertainties here, and so that the only reason that's not on the dot is because there's a little bit of variation going on, lack of precision, lack of accuracy, and the precision indicates that. Okay, so line of best fit matching the scientific theory. So that does match the scientific theory if it's just a small range here. So you haven't done a large enough range to incorporate the full relationship. There has to be some sort of explanation of why it didn't reach the max a lot earlier and then start to pull in a lot quicker. You need to describe why there's an error there and how to fix it. So there's what have I got here? Positive trend in 50. So I've already mentioned that. Just have a look at the data and see if you can find any patterns, and then explain what the errors might be. Anomalous results. You can also look for anomalous results here. You can see that this one here is not, the error bars are not encompassed over here. And so you can also have it a lot further out. Say if this one was further down here, that would look unusual and anomalous. You could decide to delete it, or you could analyze it for the error. So I've already talked about line of best fit, whether it goes through the error bars or not. That's an issue. Size of error bars. So talk about whether your error bars are nice and small. That's good, although you want it to go through the line of best fit. Large is less precise. If you're talking about standard deviation, then there's a larger spread of data is another way to say it, although that's sort of said rather more crudely with absolute uncertainty in the mean. Overlapping error bars, so you're not completely confident that there's a difference between these two, all right, because they overlap quite significantly. These two don't overlap, and so you are far more confident, especially if you're talking standard deviations, that there is a difference between the two means. So they're things you could talk about. Talk about things that are most significant, so that does require your judgment. And I haven't talked about everything. I'm just giving you some pointers. All right. Possibly a negative control. If you're doing it in this fashion, you would expect it to be to 0, or a positive control. So consider whether you've done something that should be negative. So if you're getting gas released when there's no catalase, then there's obviously an issue. That's a negative control. Or a positive control, maybe something that you know is positive and you're just testing that all the reagents work. So especially for biology, but this does definitely pop up in chemistry and physics sometimes, the use of positive and negative controls is very important. Okay, so I think that is all the main points I want to talk about this data. You have to, everything's unique and different. You basically have to put a lot of thought into it. I just telling you some pointers in this particular case that can pretty much be applied to most situations, although every experiment's slightly different and will have unique and interesting things to talk about.